Hi, everyone, and thank you so much for joining us. And we have the great honor, and we are very delighted to have Professor Geoff Hinton with us. Professor Hinton, on behalf of Morocco AI community, on all the Morocco AI scientists, researchers, it is a great honor to have you. I'm sure Professor Hinton needs no introduction, but I have the great honor to read his bio and introduce him. Professor Geoffrey Hinton was one of the researchers who introduced the backpropagation algorithm and the first to use backpropagation for learning word embeddings. Professor Hinton has invented several foundational deep learning techniques throughout his decades-long career. His other contributions to neural network research include Boltzmann machines, distributed representations, time delay neural networks, mixture of experts, variational learning, and deep learning. And his research group in Toronto made major breakthroughs in deep learning that revolutionized speech recognition and object classification. Professor Hinton received his PhD in AI from Edinburgh in 1978. After 5 years as a faculty member at Carnegie Mellon, he became a fellow at the Canadian Institute for Advanced Research and moved to the Department of Computer Science at the University of Toronto, where he is now an emeritus professor. He's also a VP Engineering Fellow at Google and Chief Scientific Advisor at the Vector Institute. Professor Hinton has many awards that I cannot list all. He's a fellow, I will just mention some. He's a fellow of the UK Royal Society and a former member of the US National Academy of Engineering and the American Academy of Arts and Sciences. His other awards include the David Rumelhart Prize, the Killam Prize for Engineering, and the IEEE Frank Rosenblatt Medal, the IEEE James Clerk Maxwell Gold Medal, and the Honda Prize, and of course, the Turing Award. It is our great honor to have you, Professor Hinton. Please, the floor is yours.
Thank you for the introduction. Okay, the talk I'm going to give today is very similar to the talk I gave at NeurIPS recently. It's about the forward-forward algorithm. And the motivation for it is to try and understand how the brain might be getting gradients. So we all know that backpropagation works extremely well. It creates things like ChatGPT, which are extremely impressive. And that raises a question of, is the brain using backpropagation or is it using some other way to get gradients? And rather than focus on making bigger and bigger models that work better and better, for the last few years, I've been focusing on how the brain is getting gradients. And to begin with, I thought the brain had to be using backprop because it works so well. And I've now come to the conclusion that it probably isn't using backprop, and possibly it doesn't work as well as big systems that use backprop. There's no convincing evidence that there's backpropagation going on in cortex, backpropagation of derivatives. And obviously backpropagation through time is implausible if you're having to deal with real-time continuous input like video. There just isn't time for the brain to stop and backpropagate things backwards through time. If you look at the anatomy of the brain, it's all wrong. So between two cortical areas, there are forward connections and backward connections. So if you order the cortical areas by how close they are to the perceptual input, there's forward connections and backward connections, but the backward connections don't mirror the forward connections. Actually, what you find is little loops. So in the lower cortical area, if you have activity in a layer in the lower cortical area, it'll go through about 6 different synapses in the lower cortical area and the higher cortical area before the activity gets back to where it started. So it looks like it's set up for doing things like autoencoding loops, but it's not set up for doing backprop. And the final argument is backprop requires an exact model of the computation you perform in the forward pass so that you can compute derivatives. And if you have low power analog hardware or noisy hardware like the brain, where the input-output properties of individual neurons drift with time, it's going to be very hard to get the gradients. So we need an algorithm that is robust to having hardware that behaves in variable ways and ways that we can't model properly. And that's what the forward algorithm is. So the other thing we know about the brain is it's highly recurrent. So if you take, for example, a mouse visual cortex, mice aren't that visual, but they do have visual cortex. And if you look at what's called the visual cortex, when the mouse isn't behaving, the neurons are driven by vision. But as soon as the mouse starts behaving, then the neurons are driven more by the motor behavior of the mouse than by the vision. But everywhere in the brain, things are highly recurrent. So it doesn't fit at all with a pure feed-forward net. Another problem with backpropagation being how we work is that the big language models that we're getting now know much, much more than we do, and they use far, far fewer weights. So backprop is really optimized for squeezing a lot of knowledge into not many weights, like only 1 trillion. For the cortex, you've got the opposite problem. You have about 100 trillion connections, but you only live for about 10 to the 9 seconds. Fortunately for me, that's about 2 times 10 to the 9. And so you don't actually have much experience compared with the number of parameters you've got. Whereas these really big language models have seen many, many trillions of training examples. So they're sort of different ends of the spectrum. Backprop, you have a small net and a lot of data. And the cortex, you have a big net and not much data. So the requirements on the learning algorithm are somewhat different. So the forward algorithm works like this. We're going to train each layer of a feed-forward network. So to begin with, we'll have a feed-forward network, but we'll generalize it to recurrent networks later. You're going to train each layer, have high goodness when it's presented with a positive data vector, that is one from the training set, and low goodness when it's presented with a negative vector, that is one that is not from the training set. And there's many ways to get these negative vectors, but the obvious way is to get the model to generate them itself, like in a Boltzmann machine where it generates its own negative data. We're going to train the layers greedily, 1 layer at a time, to begin with. And I'll describe some of the ways of generating negative data vectors. So each hidden layer is going to be composed of ReLUs. It doesn't have to be ReLUs. You could use all sorts of things, but for now I'm using ReLUs, rectified linear units. And there's going to be a goodness function, which to begin with will be equal to the sum of the squares of the activities. There are many possible goodness functions you can use. That's the most obvious one. And what each hidden layer is going to do is try and compute the probability that the input is positive data, that is real data, as opposed to fake data, that is stuff generated by the model itself or generated some other way. And so it's going to say the probability that this is positive data is the logistic of the goodness of this whole layer minus some threshold. And so we want the goodness of a layer, that is the sum of the squares of the activities in the layer, to be high for positive data, and we want it to be low for negative data. Now, you can see how you could learn 1 layer like that, but obviously after you've learned 1 layer, the activities in that layer will be high for positive data and low for negative data. So the next layer will have a very easy job. It just needs to look to see whether the activity is high in the layer before, and if it is, it says positive. To prevent that, we're going to normalize the length of the activity vector in the first hidden layer using a simple form of layer norm before presenting it to the second hidden layer. So the first hidden layer was trying to decide whether it's positive or negative data based on the length of the activity vector, the squared length, the sum of the squares. When we normalize that by making it be a constant length, then we remove all the activity that was used in the first hidden layer for classifying the input as positive or negative. So now the second hidden layer has to use some other kind of information, namely the information in the relative activities, So you can think of it as the activity vector in the first hidden layer has a length and an orientation. We use the length to decide whether it's positive or negative data, and then we remove the length by normalizing it, and we send the orientation to the second hidden layer. And what the second hidden layer has to do is take that orientation, and using its incoming weight matrix, it has to convert some of the information in the orientation into a length that can be used for deciding whether it's positive or negative data. So to begin with, I'm going to show you FF doing supervised learning. And since it's a feed-forward network and we're not doing backpropagation, it's not immediately obvious how to give it a label, because we normally put the label in at the output layer. But what we're going to do is we're going to put the label in at the input layer. So positive images will be images that include the correct label. And I'm actually going to put the label as part of the image. You can do this in MNIST because Jan LeCun left a big black margin around each digit to make life easier for convolutional nets. But it means there's some way you can put labels if you want to that doesn't interfere with the image. So positive images will have the correct label in them in the first 10 pixels using a 1 of n code. Actually, it's not 1, it's 5. I make it more active so it has more effect. So there'll be 9 zeros and 1 5 in the first 10 pixels. And negative images include an incorrect label. And so the only difference between positive and negative images is the label. Features of the image that don't correlate with that label will be ignored by the algorithm because they don't help it to discriminate between positive and negative cases. So if I were to put some random noise elsewhere in the margin, it would just ignore that random noise because the random noise doesn't correlate with the difference between positive and negative images. That's the nice thing about supervised learning. It ignores things that are irrelevant. So there's 2 ways you can test the network once it's learned. You can give it a neutral label. That is, you take the first 10 pixels and make them all equally active. Then run forwards through the network to get activities in the hidden layers. And then take all those hidden activities and make them the inputs to a softmax. So that's called a linear classifier, even though it's non-linear. And that way you can just use the hidden activities it's learned to learn a simple model that classifies the digits. And that's quick. You just have to run things through the network once. A better method, but slower, is you give the net the same image many different times, once with each possible label, and you see which label gives the highest total goodness in the hidden layers. That's what you were really training, and so that's the right way to test it. But it involves having to run it as many different times as there are labels, which is fine if there are only 10 labels, but if there were 1,000 labels, it would be expensive. And what you would do then is you'd first use the quick method to get a short list of plausible labels, and then you could sequentially check the goodness of each label in the short list. And so maybe you get the best 5 labels and check those. So it's relatively efficient, even for big label sets. So on MNIST, if you take a fully connected net and it's non-convolutional, you typically get about 1.4% test errors with MNIST, somewhere between 1.3 and 1.4 if you use backprop. With the forward algorithm, which isn't backpropagating, if you just make the negative labels, the labels you use in negative cases, you just make them be random, the training is quite a lot slower, because towards the end of training, most of the negative cases it's getting are obviously negative cases. They're not plausible labels, given what it knows already, so it doesn't learn anything. You can make it learn faster by giving it negative cases that are hard negatives. And the way you do that is as you're training the forward algorithm, you also train the linear softmax classifier that uses the hidden activities to classify images. And you look at the outputs of the softmax classifier and you pick one of the more active classes, not the correct class, but you pick from the distribution over the incorrect classes. So you pick hard negatives much more often than easy negatives, and that makes it learn much faster. And then it learns about a factor of 2 slower than backprop. And it gets about the same performance as backprop. If you jitter the images by up to 2 pixels in all 4 directions, so there's now 25 different locations for an image, and you train for a long time, you get a much better error rate of about 0.64%, which is about what you get with backprop if you jitter the images. It's also what you get with backprop much faster if you use convolutional nets. So for MNIST, jittering the images allows you to get a performance similar to convolutional nets. And you also get nice receptive fields if you do that. So I'll show you some of the receptive fields. So what you're seeing here is in the first hidden layer, the receptive fields it's learning. And you'll see in the first 10 pixels are the weights that a feature detector has to the label units. And the 2 ones in red boxes I've blown up on the right. And if you look at that top feature on the right, if you see sort of 2 roughly horizontal lines like that with black in between them, that's pretty good evidence that it's either 3 or a 7 that's got a crossbar halfway down. And it learns that. So it's learned a sensible feature. We can interpret what it's learned. And it's a very sensible feature that says if you see that, it's probably 3 or 7. And therefore it's learned big weights coming from the 3 and the 7. And that means when you put in one of those as a label, that'll activate that feature. But if you put something else in as a label, a bad label, that feature won't get so active, so it won't be so happy, so it'll know it's a negative case. So a major problem with that version of the forward algorithm is that because it's not backpropagating, what you learn in later layers doesn't affect what you learn in earlier layers. And that seems to be bad because that's one of the major good aspects of backpropagation. And it looks like we've lost it if we use this algorithm. It's particularly bad if you want to model top-down effects in perception, which I do. So here's 3 examples of top-down effects in perception. If you look at the H in the middle of those 2 words, it's exactly the same, but it's an H if you look at the, and it's an A if you look at the cat. And if you don't attend to the letter, but just attend to the whole words, you interpret that H differently, depending on the context. Similarly, if you look at the picture on the right, when you first see it, you see a face. And so that pair in the middle, you interpret as a nose. And the bottom-up data isn't really telling you it's a nose, it's telling you it's a pair, if anything. But top-down data from the whole image is telling you there should be a nose there, and that's what you see it as. So that's a strong effect of top-down information. And then if you look at the sentence at the bottom, if I give you that sentence, in a single sentence, you get a good sense of what the word scrommed probably means. It probably means she hit him over the head with it, or she attacked him with it somehow. It could mean sort of she impressed him with how well she cooked, but that's much less likely. So you get an idea of the meaning of a word from a single context. And that's another example of a top-down effect from the context, telling you how to create a vector that represents the meaning of the word scrommed. So the way we're going to make the forward algorithm deal with top-down effects is by taking a static image and treating it as a video. It's a very boring video because every frame is the same. But we're going to use a recurrent network that's designed to process video, and we're just going to give it a very boring video, which is a static image. Then the learning is greedy in time. It's not doing backprop through time, but it's not greedy in layers, as you'll see. So this is the kind of network I'm going to use. And this is taken from a paper I published last year on a system I call GLOM, that's designed to explain how a neural net could model part-whole hierarchies without having to keep rewiring itself according to the structure of the part-whole hierarchy. So in a neural net, what neurons do depends on their connection strengths, and they can't just go off and do different things on the fly. So that makes it hard to implement in a neural net flexible graph structures like part-whole hierarchies, which are different for each image you see. And the GLOM paper was about how you might implement those hierarchies by having islands of similar vectors representing parts or wholes. And it required an architecture like this in which you could learn. And when I was in the GLOM paper, it was kind of embarrassing. I didn't have a learning algorithm that was biologically plausible for this kind of architecture. And now the forward algorithm works in this kind of architecture and is much more biologically plausible. So if you look at the middle level there, level L, and you look at the right-hand box, the activity at any time in that box, that layer, is determined by bottom-up input coming from the level below at the previous time step, top-down input coming from the level above at the previous time step, and lateral input coming from the same level at the previous time step. That's in green. And so if you now think about how would I get high activity levels for positive data in that layer, then the way you get high activity level is for the main way is for that top-down input, the red arrow, and the bottom-up input, the blue arrow, to agree, to point in the same direction. Then you'll have high activity. So you can see that the forward algorithm is trying to get agreement between top-down predictions and bottom-up feature extractions. And that top-down prediction, that downcoming red arrow to the rightmost box in the middle level, if you look where it came from input data 2 time steps ago, actually 3 time steps ago, because it had to come up through level L on the left-hand side there, then up again to level L+1, and then down to level L again. So the contextual information is from earlier time steps, and it's gone through more levels of processing. And what's happening here is when it tries to get high activity in level L, what the forward algorithm is really trying to do is make the top-down activity that's based on a bigger context, but older data, to agree with bottom-up activity that's based on a smaller context, but fresher data. So it's going to have to learn to be a predictive model. So if the video is actually moving, and I've done it with moving video and it works too, as long as the movement's simple, it's going to learn a predictive model, and it's going to seek agreement between what the predictive model predicts and what you actually see. And so we're now getting top-down effects in perception. Now, those top-down effects don't propagate as fast as backpropagation. So let me just show you what it looks like for doing digits. The frames of the video are just digits, and it's the same digit every time. And at the top level, we put in a label, and it's the same label every time, using a 1 of n. Actually, it's 5, not 1, but there you go. And so that's the recurrent net we're training. And if you train this recurrent net with the forward algorithm, it works quite well. So the video pixels are the bottom layer. The top layer is clamped to the correct label for positive data and to incorrect label for negative data. We run it for 8 iterations. And to begin with, I tried to make the goodness be high. I tried to make high activity be the goodness function. So you're trying to get a big sum squared activity for positive and small for negative. It turned out it worked better to actually make low activity be the goodness function. You're trying to get low activity for positive data and high activity for negative data. And in that case, what you want is for the top-down input to be exactly the opposite of the bottom-up input. This is much more like predictive coding, where you're trying to make the top-down input erase the bottom-up input. That actually works better, and that's more like the brain. For familiar data, you tend to have less activity. When it's surprising data, you have more activity. So if you use 2 hidden layers of rectified linear units and you run for 8 time steps, and to begin with, I started collecting gradients after 4 time steps because I thought it should settle down for a bit. Actually, it works better if you collect gradients right from the beginning. And you decay the learning rate down from the initial learning rate down to 0 after 60 epochs. So it's running for 2 or 3 times as long as backprop would run. And it's also doing multiple iterations. So it's quite a lot slower than backprop. At test time, you then do the expensive way of making a classification. You run the net 10 different times with different labels and pick the run that has the highest goodness. It now gets 1.31% error, which is right in the range of what a sensible model trained with backprop will get. It seems to be slightly better than the non-recurrent net that I described before. But that may not be significant. But at least it is not significantly worse. If you try something harder, like CFAR 10, where there's a lot of irrelevant information in the backgrounds, and you run this recurrent net with either 2 or 3 hidden layers, and you use local connectivity. So I'm not using convolution. I'm not sharing weights because that's biologically implausible. But I am using local receptor fields. And the way I do that is every hidden layer has a sort of 32 by 32 layout. So a unit is sort of centered on some part of the input image. And in each hidden layer, you connect it to units that are within an 11 by 11 receptive field centered on that point in the image. And you do that for the bottom-up connections. You also do it for the top-down connections. So it's got local connectivity, which limits the number of connections and makes it generalize a little bit better. And I run it for 8 iterations using a softmax linear classifier to select hard negative labels. And if you take that same architecture, at least the feed-forward part of it, and you train it with backprop, you get about 37% error with 2 hidden layers and about 39% error with 3 hidden layers. You have to regularize it quite strongly with strong weight decay. If you do the same thing with the forward-forward algorithm, you get it's slightly worse. It's not as good as backprop, but it's close. And also, as you go to more hidden layers, it doesn't get significantly worse. If anything, it got better, but that's probably insignificant. So it works. It doesn't work quite as well as backprop. But my current view is the brain probably doesn't work quite as well as backprop, which is a little bit scary because it suggests that the digital technology we've got now is going to end up working really, really well and maybe better than us. If you think what's happening as this network is settling down, it's not doing backpropagation, but it is doing something else, which I call back relaxation. So if we go back to the picture of the network, this one will do. The information that's coming down on those red arrows is providing top-down input that's helping to train the bottom-up input. And that means information from the representation at a higher level is influencing the bottom-up input. So if you look at that middle layer, the right-hand box of the middle layer, the bottom-up blue arrow, the learning there is being influenced by what's coming down from above based on older video frames. And so you are getting this thing we want, which is that higher level representations can influence the learning of lower level representations. But if you ask how fast information gets back, well, at that middle layer, the top-down information gets mixed with the bottom-up information to arrive at a representation. And then that sort of averaged representation gets sent down to the level below. So the information from above is being diluted by the information coming bottom-up. And what you get is that the rate at which information from the high layers propagated to lower layers is much more like diffusion or relaxation than like propagation. In backpropagation, the information gets all the way back and sort of full information gets back, modified by all the weight matrices on the way, but not diluted by the activities on the forward pass. And here it's a diffusion process, so it'll work through several layers okay, but it wouldn't work at all through 100 layers. Now, fortunately, the brain doesn't have 100 layers. And what will happen here is the information won't get all the way back to early layers the first time you see an image. But the learning that you do when you see an image, you'll get the information back through a few layers. So now the bottom-up input to the middle layers will have learned to be different because of the information coming down from above. And so if I now show you the same image again, the bottom-up arrows are different. So now that difference, which was caused by the high-level representation, will cause a difference at the level below. And so if you present an image several times, the information will get back through many layers, but it won't get back through many layers efficiently in one presentation. And so that's the difference between back relaxation and back propagation. And I suspect we're stuck with back relaxation. Okay. I just wanted to finish by saying how this relates to GANs. So a generative adversarial network, like a Boltzmann machine or noise contrasted estimation, works by trying to discriminate between real data and generated data. And the discriminative model of a GAN in the forward-forward algorithm is replaced by a greedy feed-forward model that tries to make a discrimination at every layer instead of just having a logistic unit at the last layer. And because it's trying to make a discrimination at every layer and it's greedy, trained greedily, it can be trained without using backpropagation because we're making these greedy discriminations at each layer. So that's how we managed to learn a discriminative model without using backpropagation. Now in again, the generative model, which is normally trained by backpropagating the discriminative error through the generative model, we're not going to have a separate generative model. We're going to replace the hidden layers of the generative model by the hidden layers of the discriminative model. We're going to share the same representation. And we're going to use those hidden layers in the discriminative model to try and predict the next term in a sequence. So we can train the generative model without backprop because it doesn't have to learn its hidden representations. It's just stealing them from the discriminative model. And that gives us several advantages and one big disadvantage. So if you think about the problems that GANs have, they've got an adversarial competition between the generative and discriminative model, and that makes training tricky. You have to get the relative learning rates right. That disappears if the generative model and the discriminative model share their hidden representations. Another problem with GANs is they have mode collapse. So the generative model might end up ignoring large parts of the data space, but the GAN still seems very happy. And that can't happen if you share the hidden representations with the discriminative model, because now the hidden representations are trained on the whole of the data space, or everything covered by the training data. And so you eliminate mode collapse. But the big disadvantage you get is that you don't learn such a good generative model. And a big open question at present is whether using the forward-forward algorithm, particularly in a recurrent net, you can learn a good enough generative model so that the model can produce negative data that's good enough for training the forward algorithm. And that's what I'm working on now. And that's the end.
Thank you so much, Professor Hinton, for this amazing, insightful talk. So I have many questions that I'm gonna try to select some that I can ask you. So with this forward-to-forward algorithm, just opened a new kind of area of research. How do you see this influencing the creation of other architecture, other models and architectures?
Okay, I think in practical terms, backpropagation works better on current digital computers. But the forward algorithm might allow us to use pure analog computation. So the problem with analog computation is it's noisy, stray electric fields influence the results of the computation. And as a result, you can't make two different analog computers behave exactly the same way unless you keep digitizing things as you go. And of course, as soon as you start digitizing things, you lose all the advantages of analog. You have to use high power, and 1-bit digital might be okay, like the brain does, and spike or not spike. But getting like a 8-bit or 16-bit number is a crazy amount of energy compared with pure analog computation. The advantage of the forward algorithm is you can run it in hardware where you don't know how the hardware works. So, for example, if I put in a layer that's just a random matrix followed by rectified linear units, or followed by any other kind of unit I like, and I put that in the middle of my network, and I don't even know about it, and I run the forward algorithm, it'll work just fine. It doesn't have a problem. Whereas if you have a layer in the middle of a backprop network, a feed-forward network, where you don't know what the transformation is, and maybe the transformation is not even stationary, the backprop algorithm doesn't work. The best you can do is try and build yourself a differentiable model of that black box that's in the middle of your net. But the forward algorithm, it just doesn't slow it down at all. It has no problem. And that seems very promising if you're having to work with hardware where you don't know exactly how it's going to behave. You know roughly how it's going to behave. You need to know enough about it to know how to change your incoming weights to be more active or to be less active. But that's all you need to know in this algorithm. So you need to have some units in the network that can change their incoming weights to get more or less active. But you have lots of other stuff going on, and it'll just adapt to it. And it's because the two different forward passes cancel all these things out. And there's a very important issue here, which is doing a contrast between positive data and negative data allows you to cancel all these things out. As soon as you try and do your contrast between two internal representations, like you do in typical contrastive learning at present, you get big problems with all these stray effects. But there's a wonderful property that happens if you use positive data and negative data, which is all these internal noises and uncertainties. They all cancel each other out because they're the same in the forward and back, in both forward passes.
This sounds very promising for hardware. Then do you see this being adapted for, let's say, GPUs and TPUs and all?
No, I see it as a completely different kind of hardware, which I call mortal computation. So if you look at the history of computing, when they first made general purpose digital computers, everybody assumed that the way you get it to do a specific task is by writing a program that tells it exactly what to do. Now that we have good learning algorithms, you can get a general purpose network to do specific tasks just by learning. You don't have to write a program. Obviously, the learning algorithm has to be in there, but you don't write a program for each task. And I think that suggests that we could get rid of one of the basic foundations of computer science, which is the distinction between software and hardware. So if you can separate the software from the hardware, you can have a computer science department where you talk about the properties of programs without knowing any electrical engineering. If you can't separate them, you have to know about electrical engineering as well as programming. Also, if you can separate the hardware from the software, you can put the same software on millions of different cell phones. So it's very convenient. Also, you can prove things about what the program does. I'm suggesting giving up on all that. If you look at biology, it didn't have the same constraints. And if you go in the other direction, you say each piece of hardware is going to be different from each other piece of hardware. It's going to be somewhat different in its details, just like your brain and my brain. And the weights that you learn are only going to work in that particular piece of hardware. And they're going to be adapted to the particular properties of the particular neurons in that piece of hardware. Or if it's analog hardware, the particular properties of those particular analog circuits, which aren't the same in each piece of hardware. So now you have a big problem that you have to train each piece of hardware separately. They have to be educated, just like people. And you can get information from one piece of hardware to another piece of hardware by using techniques like distillation, which is a form of education. But you can't just copy weights across. And my current belief is there's a tremendous win from being able to just copy the weights across. And that's what makes backpropagation in our current digital hardware. That's what means it's going to be better than us. But if you want to have low power, then it's worth exploring analog hardware where you give up on the separation of software and hardware. Each separate piece has to be trained, but then it can run. Then you can run something with 100 trillion connections for only 30 watts.
Do you see AI going on this direction of actually separating software and hardware? I mean, we already know that usually now we do optimization on software and then we try to do optimization on hardware as well. What's your stand?
I see there being a bifurcation. This frontier where you use current digital hardware and clever programming, and you share weights, so you get model parallelism. Sorry, you can train the same model on different data on different computers and then average the weights, things like that. That's going to be where devices get the most intelligent. But there's going to be a completely different kind of device, which is these analog low power devices, whose main advantage is that it's going to be cheap to fabricate the hardware because it doesn't need to be fabricated reliably. You won't need a $10 billion fab line to make the hardware. You'll actually grow it with nanotechnology. And it's going to run at very low power. So you're going to be able to have a language interface in your toaster for $1 running at a few watts. But it's not going to be as smart as these really big, very expensive, very power-hungry systems trained with backprop. That's my current belief.
Super promising, and it's great to hear. Maybe one last question regarding the presentation. Do you see this as a new area maybe of research, because it's very different than the way how we used to do things like backpropagation? So do you feel that this is going to give birth to like new different ways?
Well, this isn't giving birth to it. There's already people who have all these beliefs. There's a guy called Jack Kendall who works for a company called RAIN, and there's a group at Stanford who believe all this and are trying to do analog hardware. And this algorithm is very relevant to them.
Okay, and I have a question here. You are very optimistic about that we always are getting closer to learning how the brain works. So what are some of your latest discoveries about the brain that have changed your way of thinking about it? I think you said that last time maybe we will figure out in 5 years or so. Do you still feel that we are close?
I always think we're going to figure it out in 5 years or so, and eventually I'll be right. It's just that saying we're not going to figure it out for 100 years isn't a very good research strategy. It may be a bit more realistic, but if we're not going to figure it out for 100 years, you might as well give up. It's clear we're not going to figure it out in the next week, but believing that we may well figure, and the reason I think we may figure it out is because once you get close enough, there'll be a big attractor. Once you get close enough, suddenly all sorts of things will start making sense. All sorts of weird facts about the brain will start making sense. And So it's a bit like the singularity in that there'll be this sudden effect that you've got close enough, so now you can see how it all fits together. And that's what I'm hoping will happen, and I'm hoping I'll live to see it.
One last question, and this is I mean, there are so many other questions about like brain and backpropagation. This one is about actually Morocco and AI. So I have this question that there is a lot of good momentum in AI in Morocco, and MoroccoAI, we strive to have like a strong presence in all these top ML conferences and innovation. Yet for all these developing countries, there are many challenges, like the resources, right? Resources from one end, or maybe just good mentoring by qualified academics. So what is your advice, Professor Hinton, to all these AI researchers for Morocco, for it to lead Africa or just help out on AI advancements and breakthroughs?
So I'm not sure I have any very specific advice. Jeff Dean at Google is very keen on helping Africa. I mean, he got a Google lab set up in Ghana. And in general, I think a lot of the academics and leading researchers in industry are keen to help Africa. They recognize that there's a huge amount of talent there. My friend Terry Sinofsky, who's more of a biologist than me, explained to me that if you look at genetic diversity, there's more genetic diversity in Africa than the rest of the world put together, because people have been there longer. So there's a lot of reasons for wanting to help Africa, including all the bad things that imperialist countries like the one I came from did in the past. So I think you'll find that there's a lot of academics keen to help by, for example, giving talks at your conferences.
Another one was like kind of like if there is any specific like research areas that you would suggest, for example, for them to look into, depending on where they're located, for example.
Obviously, one thing is there will be, it's clear to everybody now that neural nets trained with backpropagation are working so well that they're going to be used for everything. And in Africa, there's probably lots of interesting applications that are specific to Africa. And those are going to be places where African researchers have an edge. They can understand the application and work with people who need that application. So that seems like an obvious thing to do. I haven't really thought about what else, but the most obvious thing is think about applications that are specific to Africa and work on those. And that's obviously a sort of virtuous circle.
And maybe, as you mentioned earlier, if this compute changes, right? So right now we see like this compute as all these big companies, you know, so maybe if there is areas of actually just working on problems with much less compute and still innovate there, that can be a very maybe promising area.
Well, that's what I do. I don't use, I mean, I'm at Google, so I could use these vast computing resources, but I'm also old, so I don't like learning new languages. I'm very slow at learning new languages. So actually, I decided to do kind of basic research on how the brain might be getting gradients. And that doesn't require, to do the basic research, you don't require lots of computation. You do require it if you're pushing the frontier, like these big language models. That just requires a lot of computation. And that's one of the reasons I chose to work on trying to understand how the brain might be getting gradients, which I don't think requires huge resources. It just requires good ideas.
Amazing. Professor Hinton, thank you so much for the talk. It's been a great honor to have you on behalf of the whole community, on behalf of MoroccoAI. We were so happy and delighted to have you share this very recent work of yours with us. And I hope you will hear about some great AI research coming from Morocco very soon.
And in 4 years' time, I hope you beat the French.